Good morning, chemistry humans. I've got a quick one for you here today. I just want to review one concept that you should already have experienced mathematically, and then introduce two very short topics that we're going to discuss more in your cohort classes. So most of this is just a simple preview, and then when you're in small groups, we'll dig into things a little bit more. But these are tips that can help you with some common chemistry math techniques, things that we see regularly. As you're going to see, they're not sophisticated, but I want to raise your comfort level on these basic techniques, make sure that math is as little of a barrier to you, hopefully no barrier at all, as we can manage. There we go. All right, so ratios are a fundamental part of chemistry. We do them all the time. In many ways, in fact, even a percentage calculation is a ratio. I want to make sure that you have a very clear process for what a ratio means, so that when I ask you what for a ratio in a lab in particular, you know exactly what to do to solve it. Right, so first of all, a ratio in this class is a fraction. It's important for you to understand that. It is not a little colon method ratio like 2:1, meaning a 2 to 1. Instead, we would write it as a fraction, 2/1 as the ratio. When you write them as a fraction, of course, that helps mathematically because it tells you exactly what to do. And what to do when you have a fraction is divide. And so that's important for you to understand as we go into this. So if I say the ratio of A to B, right, it means A divided by B. If I say the ratio of girls to boys in a particular class, it means girls divided by boys. The ratio of boys to girls would be the reverse, boys divided by girls. So division is always a part of it. And furthermore, it is not enough to set up the fraction, right? And so if I ask you for the ratio of 3 to 5, it's not 3/5. The answer would be 3 divided by 5, which is 0.6. I want the decimal form of that. So a ratio is a two-step process, although both steps are simple. You set it up as a fraction with A, the first thing mentioned in the ratio, on the top, and B, the second thing in the bottom. So the ratio of A to B, so the of goes on top and the to goes on the bottom. Right? And then you actually divide out that fraction to get the decimal version. And so for some people, it's a little weird saying like a ratio of 0.6 or a ratio of 2.3 or something along those lines. But that is the correct way to do this scientifically and also statistically. So you'll see that in a lot of other classes going forward in your educational career as well. And just a basic reminder that if I have a fraction, right, if the fraction is equal to 1, of course it means the top and bottom of the fraction are the same. If the fraction is greater than 1 in its total value, it means the numerator is greater than the denominator. And if the fraction is less than 1, it means the opposite. So the top is less than the bottom of the fraction. That's an important thing to know when you're calculating those. Not only can it help you spot mistakes, but it helps you with your interpretation of ratios as well. A percent is actually a ratio as well, and then the final answer of the percentage is multiplied by 100. The term percent, if you didn't know that, comes from money, as you might expect, meaning out of a dollar or cents out of a dollar. And so it's a comparison tool. So everyone knows that there's 100 cents in a dollar, hopefully, in America. And so when we say percent, it means in comparison to money. What would this be in cents out of a dollar? With 100% being the total amount or the maximum in most cases, although there are some exceptions to that as well. So if we're talking about what percentage out of the total is one component, right, then that percentage can never be greater than 100%. And that's true in many, many labs. So for example, there is a maximum quantity that you can actually produce of a chemical in a lab. And then we might ask you, what percentage of that maximum did you produce? If you got more than 100%, something clearly went wrong because you cannot produce more than the maximum based on the materials that you had, how much of the materials you were putting in there. However, when a percentage indicates a change over time, if something increases over time, then that can be greater than 100%. So if I have a certain amount of money and I invest it, and I earn 10% interest, then my total amount of money would be 110% of what I originally had, right? And so percents over 100 represent an increase, and percents less than 100 can represent a decrease. So that's why it's very important to understand whether you mean a percentage out of a total or whether you mean a percentage change over time. And so be careful with the language and make sure that you read clearly and know which type of those that you're doing. We practiced percents a little bit in the measurement lab when you did a percent error, and you'll see them again just a little bit in the packet. It's fairly common technique for us to do percents. But again, they are fundamentally a ratio. If I say to you, what percentage is a certain thing of this total, right? The is would go on top and the of would go on the bottom, right? So percent equals is over of, and then times 100. So the decimal version of the ratio times 100 is all we're talking about in the percent. Right? An example of a ratio is density. Right, and this is what you are actually doing in the second part of your measurement lab, if you didn't already know that or figure that out as we're going through it. Density is the ratio of mass to volume. And it is a constant for any given substance. And so the density, or this ratio of mass to volume, should be constant. Now, data in the lab is always a little wonky, and so your line in your graph might not have been perfectly straight. That's okay, because as long as we can see that it's close to a straight line, that is sufficient for us. All right, so a typical unit for density would be the unit of mass over the unit of volume. This is what we call a compound unit, which means that there's more than one base unit included together to make a more complex unit. We see these all the time. So for example, if you're driving in your car, the unit for speed in the car is miles per hour, or miles over hours. And so that's another example. All speeds or velocities have that sort of compound distance over time. The same thing is true here in density. It's mass over volume. So the unit for mass is grams, or kilograms if we're talking about a larger object. And then the unit for volume is milliliters or centimeters cubed, which are the same thing, again, emphasizing that for you. And so grams per milliliter or grams per centimeter cubed are the exact same thing. There's no difference between those two, and you can interchange between them without having to change any of the numbers. Sometimes we do see other volume units. So with gases, which typically have larger volumes than solids or liquids, we can see that liters is often used in there. If you look at the reference tables that I provided on Canvas, and that there's also in the classroom for you to pick up, then you can see some densities on the first and second pages, or the front and back of the first page. You can see the different units that they have. All right, and so if we have two materials mixed together, the one with the greater density will sink to the bottom. All right, so when we talk about things that sink or float, what we're actually talking about is density. Some people talk about something being heavier, right? Talk about being heavier than water, or if a substance sinks in air, we talk about it being heavier than air or lighter than air, like helium. It's not really heavier or lighter, it's denser, or more dense or less dense, depending on how you're talking about it. Density is what determines whether something sinks or floats when it is immersed in another substance. So if, for example, I put something in water, right? If it's more dense than the water, it will sink. If it's less dense, then it will float. All right, and so the density of water is actually 1. That's actually how both grams and milliliters are defined in many ways. Grams, 1 gram is the mass of 1 cubic centimeter of water, and then 1 milliliter is the volume of 1 gram of water. That's a little bit circular if you understand the units, but these are interconnected units. A lot of things that we study are actually originally defined by the values for water for those substances. And so if the density of water is 1, then it's a perfect reference point for us. Anything with a density greater than 1 will sink in water, and anything with a density of less than 1 will float in water. All right? So that's a little review of ratios and a specific example. We will come back to density again in week 3 in the matter discussion that we'll have. And there's a little practice late in your packet. For right now, though, that's just an introduction and an example of a specific ratio. There's your formula for density. D equals m over v, or density equals mass over volume. And you should know that this formula is in your reference tables as well. On the second page, all the formulas that we will use or could use in the course are in that formulas page. But in reality, although it looks very extensive, we only use 3 of them very regularly, or really at all. And finally, one last note, proportions are a little bit different from ratios. Even though they have fractions, a proportion is two different fractions that are equal to each other. And this can lead to some confusion in this course because we have a few things that are proportional. So they are set up with fractions and an equal sign between them. And that is a proportion. You can solve proportions by cross-multiplying. And if you don't know that technique, I will show it when we get to that in Unit 3. We have things that are proportional in Unit 3. However, we also have formulas and problem-solving techniques that involve fractions that are multiplied against each other, which is not the same thing. So if two fractions are equal, then it's a proportion, and you can solve it that way. If two fractions are multiplied, there's a totally different process, which is something that we'll model later on in this unit as well. Some things are not proportional, so you can't just set up a proportion. A lot of people like proportions, but if something is not directly proportional, then you can't solve it that way. Some things are inversely proportional, and some things have a more complicated mathematical relationship, so proportionality doesn't work. So just be aware of that. Right, when it comes to solving algebra, and there will be some solving of algebra, like the density equation, where with D equals M over V, you will have two of those three numbers. So for example, if I measure the mass and the volume, then I can plug them into that equation. Mass divided by volume, and then I can solve for D, the density. We could also rearrange the equation to solve for M, and we could rearrange to solve for V. It all depends on what I'm being asked to find, and we'll practice that later on in the unit. When you have to rearrange an equation to solve for one of the variables, and there will always be only one, and there's no squared terms or anything, so this is on the simpler side for algebra. When you have to solve an equation for a variable, I recommend that you solve the equation first while it's still in its symbol form before you plug in any numbers for the variables. And I'll model this for you when we solve problems over the course of the year. So rearrange the equation first in letter form, so to speak, in symbol form. And then once you have the variable isolated by itself the way that you want it to, then you put the numbers in for the rest of the variables that are in there and then simplify. So just to be clear on my terminology, because I'll use it a lot, and hopefully this is the same terminology that your math teachers in the past have used. But to solve the equation means to rearrange it to isolate one term or one variable in the equation. Right? So if I'm solving for x, it means I want to get x on one side of the equation and everything else is on the other side. To simplify means to put the numbers into the equation, and then you'll actually perform the mathematical operations, right? So that might mean multiplying or dividing, adding or subtracting, whatever the equation tells you to do. But some people refer to that as plugging in. You plug in the numbers and then simplify the equation. So solve to get the variable by itself, and then simplify by putting the numbers in. In reality, you can do it in the other way. You can simplify first by putting numbers in, and then solve for the variable. But that can lead to some problems later on in this course. And I've found that students make more mistakes in that way than if they solve first and then simplify. So that's my recommendation for you based on experience. All right, so I have one other topic that I want to introduce, and this is what we're going to do in your cohort classes in week 2. So starting on Thursday the 27th, we're going to be working through this in small groups. Make sure that you see how it works, and we'll practice it together before you go on to do the rest of it for homework asynchronously. Whenever we make a measurement in the lab, there's some uncertainty with it, and hopefully you've already seen that very clearly in the measurement lab. There can be uncertainty even in the electronic or digital balances because the last digit can be off by 1, plus or minus 0.1 or plus or minus 0.01, depending on the balance. So that last digit might be off by a little bit. That's also true, that's especially true when we're using some sort of scale that we have to read with our eyes, like a graduated cylinder or a ruler. And so if you were to look at some of your classmates' measurements based on the views that I gave you in the measurement lab, you might find that you have different answers than some of your classmates do. And that's an error that's been introduced there. Two different people reading the same water level on a graduated cylinder might not get the same number. And so therefore, there's a little bit of error. There's some uncertainty in there. The last digit is where the uncertainty occurs. So hopefully you've gotten all the other marks right. And this ties into like the bar that we were measuring the length of in the measurement units notes that you had earlier on in this course. In the measurement notes, I had a series of pictures of a black bar that you were measuring, and I noted that the 2 is very certain because it was at least 2 centimeters long, and the 0.6 was very certain. We know for a fact that it was at least 2.6 centimeters long, but the uncertainty was in the 3rd digit of it because it's between the marks, and so we had to estimate in that. Okay? Even if you think something is directly on the mark, you might be wrong about that. And so you might put 2.60 to indicate that something is exactly on the mark for 2.6, but it might actually be 2.59 or 2.61. And so the last digit of every measurement that we take should be regarded with a little bit of skepticism. There is uncertainty in that last digit. But when we have uncertainty in our measurements and then we make calculations with those measurements, then that uncertainty can propagate through our calculation, meaning that it can spread, and in some cases it can multiply and increase. And so small errors in our measurements can become very large errors in our final calculations, in the answers. And so it's important for you to understand how to fix that. And the way to fix that is through a technique known as significant figures. The other term is significant digits. They're interchangeable, and I use both of those terms as we go through, so I want to make sure you understand them both. Significant figures is often abbreviated sig figs, which I use as a shortcut. If I say significant digits, it's abbreviated sig digs. Same idea. All right, so significant figures is a way of counting the correct number of digits in a measurement and then applying that to your answers when you calculate. So after a calculation, you can round off to the correct number of digits if you follow the system. And by rounding off correctly at the end of a calculation, you eliminate as much of the error and uncertainty as you can in your number. Now, this comes from the experience of multiplying or dividing numbers in a calculator and getting a whole bunch of digits. Everybody's experienced that. You multiply like a 3-digit number times a 4-digit number, and you end up with 11 digits in your calculator screen. Most of those are garbage. They are sort of a byproduct of the multiplication, and they don't mean anything realistically, and they can be very far off from what the actual digits in those places should be, as error can multiply through the calculation. And so for that reason, we need to know how to round off. All right, so when it comes to significant figures, and again, this is what we'll practice in your cohort, so this is just an introduction. There are several rules for significant figures. Now, first of all, any digit that's not a 0 is automatically significant, right? And what that means is it will count, and then that will be applied to where we round off when we go to the end. You'll have to see how this works in practice in your class period to fully understand it. All right, so that means only the zeros are really in question when we go to these numbers, when we go through and figure out where to round off. All right, so when it comes to zeros, there are 3 rules fundamentally. Okay, and I've got the last rule broken up into 2 parts. So that's why there's 4 bullet points here. All right, so first, zeros between other digits are significant always. Right, and I know this may not be making 100% of sense why we need to know whether they're significant. That comes in the second step of this. For right now, I just need you to be able to recognize which digits are significant, which is simply a counting process. All I need you to do is to be able to count the significant figures or the significant digits in a number. And that's what we'll practice. All right, so I call the first rule under rules for zeros, I call that the sandwich rule. So zeros that are sandwiched between 2 other digits, 2 non-zero digits, are significant. So if I have the number 507, 507, right, all 3 digits are significant because the 0 is sandwiched between 2 non-zeros. Right? Zeros at the beginning or left side of a decimal. It's very important for me to clarify this. When I say the left side of a decimal, it doesn't mean the left side of the decimal point. Right? It doesn't really matter where the decimal point is. It's zeros at the left side of the number. So in other words, leading zeros, zeros that are at the beginning of the number before the first non-zero digit. It doesn't matter if those zeros are before or after the decimal point. The only thing that matters is that there is a decimal point in the number. That's how I define a decimal. It's a decimal if there's a decimal point in the number. If there's not, then it's a non-decimal. So in any number that has a decimal point, any zeros that come at the beginning of the number before the first non-zero digit are not considered significant. I'll show you why when we get into things a little bit more, and I have some help videos that show this as well. But the main reason is they disappear when you convert to scientific notation, and that's why they're not significant. Now, the zeros at the right side are a bigger problem because there's actually two different situations when this can occur. And so we have to break this down into greater details. All right, so we have zeros between other digits, the sandwich rule, those are significant. Leading zeros at the beginning of a number are significant if there's a decimal point, and really you don't see them in any other circumstances. So that's kind of an unnecessary qualifier, but it's an important definition. Finally, zeros at the right side of a number that's a decimal are significant. So any zero that's at the right side of a number that has a decimal point in it, anywhere, we count those zeros on the right side or at the end of the number. Okay? Doesn't matter if they're to the right of the decimal point or to the left of the decimal point. The only thing that matters is that there is a decimal point and then the zeros are on the end of the number or the right side of the number. Those do count towards the total. So if I put 1.70, right, there's a zero at the end of the number, right, and there is a decimal point. So that zero is counted. That would be 3 significant digits in the number. On the other hand, if I put 480 with no decimal point, then that's a different circumstance. And that's what we have right here. Zeros at the right side of a non-decimal don't count. And again, a non-decimal means it doesn't have a decimal point anywhere. So again, if I have 1.60, that zero counts because there is a decimal point. If I put 480, that zero doesn't count because there's no decimal point. If I put 480.0, so 480.0, all of a sudden the zeros both count because the decimal point is in the number. And so there would be 4 significant digits. Those are the rules for significant figures. We will apply them in greater detail down the line, right? And it's also worth looking at one more thing here about how we round off. And so this is the second stage. We will barely touch on this in Unit 1. So again, this is an introduction, but I want you to see it so that when it comes back down the line in Unit 3, we can talk about it a little bit more and hopefully it will be familiar. When you add and subtract numbers that have some uncertainty, like measurements in a lab, right, you're going to count the number of decimal places in the number, and you're going to round off to match the smallest number that you were given. If you're multiplying and dividing, however, that's when significant digits or significant figures come into play. And that is mostly what we do. We multiply and divide nearly everything. There's only one situation in chemistry where we add regularly. Multiplying and dividing means that you will count the total digits in your measurements. So if I am measuring two numbers like mass and volume from the measurement lab, okay, I measured two numbers, I would count the digits in both of those measurements. And if I have 3 digits in both measurements, then I would want to round off my calculation, the density, to 3 digits. Right? So I would round off to match the numbers that I was given. If I have only 2 digits in my measurements, I would want to match those 2 digits with my answer. So the number of digits you're given, or the number of digits that you measure by your instrument, determines the number of digits that you can keep in your final answer. What if the measurements don't agree? So what if I have a measurement that has 3 digits, and then I have another measurement that has 4 digits? So like a mass that has 4 digits, but a volume that only has 3 digits. When they don't agree, you take the smaller number of digits, because your answer to a calculation cannot have more information than one of your measurements that you started with. It cannot be more accurate than the limitations of your measurements. If I have a measurement that can only give me 3 digits of accuracy, then I can only use 3 digits of accuracy in my calculations. Now, I know that probably sounds a little foreign to most of you, and until you really practice it, which we'll do in your cohorts, it's a little difficult to understand that. There's a few more links here, which I will double check since in the last lecture the link was actually dead. But there's a few more links here for you that you can use to follow through. And then after we practice this in your individual cohorts, hopefully it will click for you and you'll be able to follow up and finish the work. That's it for today. I will see you in your cohort classes, and we'll work on this as much as we possibly can going forward. Significant figures are important in labs, but they're not hugely important in everything that we do. And so we're only going to spend a class period plus a little extra practice on it before we move on to something in week 3 that is more important and is used more frequently in chemistry class, not just in labs, but in our regular work as well. All right, thanks for your attention today. Hope you have a good day.